Hi, the SI meteorologist Paul Dorian here with a brief discussion on a weather phenomenon known as cold air damming. It plays a vital role in many wintertime or early spring ice storms or snowstorms here in the mid-Atlantic part of the U.S. And it is an important feature that is hard to model, hard to forecast, but plays a vital role, as I said, in snowstorms and ice storms here in the mid-Atlantic part of the country. We'll go over a couple of examples in the past of cold air damming situations, and let's now talk about some of the characteristics associated with this. First of all, the main point to make here is that cold air damming here in this part of the country usually involves a strong high pressure system to our north, to the north here of the Mid-Atlantic region, let's say up in the northern part of New England or even southeastern Canada. And that high pressure area interacts with the local topographic features here. We of course have the Appalachian Mountains, the Adirondack Mountains, and the interior sections of the Mid-Atlantic region and the northeastern part of the U.S. And the combination of a strong high to the north with those mountains actually can lead to what we call cold air damming situations. What happens is the clockwise flow of air around a high pressure system will send some dense cold air down the coastal plain, right along the coast, the low-lying areas, let's say the I-95 corridor, east of the Appalachian Mountains, often in the winter or spring. And again, this is often the situation when there's a snowstorm or an ice storm in the Mid-Atlantic region. Oftentimes we've referred to as the need or requirement for a strong high pressure area to the north to get a snowstorm here in the Mid-Atlantic region. And what that eventually does is it leads to cold air funneling down the coastal plain that, of course, is required for a snowstorm to occur here. And the clockwise circulation around that high brings north to northeast winds in the northeastern part, and oftentimes that cold air will just bank up along the Appalachians. So you may have temperature differences across the state of Pennsylvania, for example, from Pittsburgh to Philadelphia on the order of 20 degrees or so, where cold air gets banked up east of the Appalachians, which cut through the central part of the state. And Philadelphia might be in that cold, dense air, whereas Pittsburgh might be in the area where some warmer, lighter air can actually infiltrate the area. So again, there can be some significant temperature differences in a cold air damming situation across the mountain chain here in Pennsylvania. That means from southwestern PA to southeastern PA. We'll go through a couple of example snowstorms in the past that had a distinct wedging pattern associated with temperatures or the pressure, isobars, that are often detected during cold air damming situations. Now again, I mentioned at the top that some of the mesoscale models still have difficulty with a cold air damming situation. There's all kinds of factors that play a role, including the temperature pattern as you go up from the surface into the upper part of the atmosphere, because just a small change in the thickness of a warmer layer, for example, can mean the difference between freezing rain, sleet, or snow. So cold air damming is still being studied in all the universities and all the scientists, and it plays a vital role in many snowstorms or ice storms here in the mid-Atlantic part of the U.S. Well, before we take a look at a couple of classic examples of cold air damming snowstorm situations here in the Mid-Atlantic region, let's take a look at a Google Earth map just to kind of focus in on what we're talking about here. We have the Adirondack Mountains here and the Appalachian Mountains here. They kind of run inland across like central Maryland, central Pennsylvania, then cutting through the interior sections like this. And what generally happens in a cold air damming situation is strong high pressure may develop up in the north of the Mid-Atlantic region, such as in the northern part of Maine or even southeastern Canada, and a clockwise circulation around that high will funnel some cold air right down the coastal plain in a fashion like this. Again, we talked a little bit earlier about north to northeast winds will set up. We'll have this cold air damming situation, and the cold air tends to bank up right along the eastern part of the Appalachian mountain chain. So again, there can be significant differences in a cold air damming situation from the temperatures, let's say, across Philadelphia to Pittsburgh. Now, on the western side of the mountains, you can get some warmer air that moves in from the south and west and can affect the surface temperatures around Pittsburgh. But it's kind of, since it's such a lighter, less dense air mass, it's kind of lifted up and over the Appalachian Mountains and has a hard time of affecting the surface conditions down east of the mountains, but it can affect the upper part of the atmosphere, which can lead to ice storm situations, anywhere from freezing rain to sleet, as well as in snowstorms. The cold air damming does play a vital role. Well, I thought I'd show a couple of examples of surface maps along with upper air 500 millibar maps associated with some classic cold air damming situations. And we'll focus in on snowstorms here. Again, cold air damming is crucial in ice storm situations, but there are also events that occur during snowstorms. And these are two classic snowstorms here in the northeastern part of the country. This one from February 10th, 1983, and the next one we'll look at is from January 1996. And right here, this is from the Penn State eWall site. This is the surface map in this particular cold air damming situation, where again we have this tremendously strong high pressure area, 1032 millibars, in this case up in southeastern Canada. Now notice here the black lines here have kind of a kink in the pattern here. This is noted quite often with very strong cold air damming situations. Again, the clockwise flow of air is sending cold air down along the coastal plain, and the pressure pattern as well as the temperature pattern can tend to set up like with this kind of a wedging shape here. So the cold air comes down here, and warmer air can actually ride up and over the western side of the mountains, and again warming places like southwestern Pennsylvania, whereas southeastern Pennsylvania stays in the cold air. So this little kink, in this case, this is the pressure pattern right here. This is a characteristic of a cold air damming situation in this part of the country. By the way, cold air damming can occur in other parts of the world, especially where there have to be mountain chains. And for example, just on the east side of the Rocky Mountains, let's say in Colorado, you can have cold air damming situations just like here in the mid-Atlantic part of the country. Here's example number 2 from another classic snowstorm, January 7th and 8th, 1996. And here you go, you have this high pressure. In this case, it's what we can often refer to as kind of a banana high, that it extends all the way from the northern plains into the southeastern part of Canada in kind of the shape of a banana. So you can have high pressure situated up here, sending cold air down the coastal plain here in the mid-Atlantic and northeastern part of the country. And here again, you have this characteristic kink in the isobars right here, indicative of a cold air damming situation where cold air goes all the way down, sometimes as far as the Carolinas, even farther south than that. And you can have warmer air moving up into the Ohio Valley, but it will not dislodge this cold, dense air east of the mountains, and hence you will have frozen precipitation either in the form of snow or ice or freezing rain on the east side of the mountains in a cold air damming situation. Again, these two examples are from tremendous snowstorms that occurred in the mid-Atlantic region. Now, another characteristic of a cold air damming situation can be seen at the upper part of the atmosphere. We're going to take a look here again from the Penn State eWall website for these two particular snowstorm situations, the 500 millibar map. And what is often the case is a confluence pattern where that high pressure system sets up. In fact, it all plays a role in the development of the high. By confluence, I mean some kind of convergence here. You see the wind generally flows along these lines here at 500 millibars, and in this particular case, they tend to converge in this fashion here in this part of the country, or southeastern Canada and northeastern part of the U.S. And in fact, confluence or convergence in the upper part of the atmosphere leads to difluence or divergence in the lower part of the atmosphere, and that is the development that leads to the development of a high pressure area. So in a cold air damming situation, look in this part of the world, the southeastern Canada or the northeastern U.S., for this confluence at 500 millibars, and you'll often find strong surface high developing, and that can lead to that cold air damming situation. So this is the February 1983 snowstorm. Let's now take a look at the upper air pattern for the January 96 snowstorm. And here it is, and again, that kind of characteristic confluence in the upper part of the atmosphere where you have a couple of lines coming together like this, and you have this confluence in the upper part that leads to a surface high development here in the lower part of the atmosphere, and that is a characteristic of a cold air damming situation. So we've looked at a couple of classic snowstorm situations, one from 1983 and another from 1996, both of which had very strong high pressure systems to the north that led to cold air damming situations. Again, this is a weather phenomenon in the northeastern part of the country. It can occur elsewhere, but it's certainly noted for many snowstorms or ice storms in this part of the country. That's it for now from the SIweather.com. This has been a brief discussion on cold air damming. I'm meteorologist Paul Dorian.